Hello again, my dear students, and welcome to a new chapter in our PV grid connected module, postgraduate module. In the previous chapters, we have demonstrated a very critical and important block in our PV system, which is a DC-DC converter. Either from an electronic perspective related to the buck boost and buck boost behavior, or from the controlling perspective related to the maximum power point tracking through a duty cycle. Now we are going to shift toward another important block as well in our system, which is a DC-AC inverters. So let's now start sharing presentation slides concerning DC-AC inverters. And maybe the first important question to be asked on this chapter is why we need a DC-AC inverter. And actually, the answer will come from the load side. The load is the driving force toward a DC-AC inverter if needed. Herein, as you can easily observe around you, most of our loads are AC loads. That's why, or that's because simply our grid utility provides us an AC signal. Accordingly, manufacturer design loads to be driven through an AC. This including chargers for laptops, mobiles, lighting loads, air conditioning, and all other types of loads. That's why having a DC generated energy is not sufficient or is not compatible with the current available loads around us. And based on that, a need for a system that can convert a DC into an AC becomes something very essential. So our block to be investigated today is a block that converts a DC energy, a DC power, into an AC power. And based on the power balance equation we have already investigated in DC-DC converters, we know that, ideally speaking, input power should be equal to the output power. Of course, realistically, this will not happen, and we will have, again, an efficiency term that expresses the efficiency of your device, which is definitely below than 1 or below 100%. But ideally speaking, what you input should be equal to what you get as an output. Now, the main difference between a DC-DC converter and a DC-AC inverter is the nature of the power. In DC-DC converters, you input a DC power and you output a DC power. So simply, V input, I input equal V output, I output. However, now in a DC-AC inverter, you are inputting a DC signal while the output is an AC power. So let's revise quickly. What is the difference between calculating an AC power and an DC power? DC power, I think you already can know this, as DC power is voltage time current, or I square R or V square over R, which is a normal way of calculating power, as we already did, either with the PV modules or with the DC-DC converters. However, whenever it comes to AC, I mean, whenever your input is now alternating with time, then a new parameter appears in the equation, representing the lagging angle between the voltage and the current, termed by theta. So now it becomes V times I times cosine theta, where we define this cosine theta as a very famous term in electrical power by the name power factor. So you can say now that the power equals to voltage times current times the power factor or cosine theta. This is simply comes from the information that now you will have a complex component of power. Your power will include a real component which can be reflected by cosine theta, and an imaginary, or what we can call an apparent power, which is reflected by sine theta. So in order to get the real component of your power, you have to multiply the power by this cosine theta factor, which represents the power factor. The next question will be how we can convert a DC signal to be an AC signal, which is simply the function of a DC-AC inverter. Of course, there is a lot of electronic tricks and electronic structures that can be implemented to be used as a DC-AC inverter. But what we are going to demonstrate now is the basic principle beyond a DC-AC inverter. A very basic principle, I'm sorry, before that, maybe I forgot one slide also to be mentioned here related to the nature of an AC. So in an AC signals, I think this is a general information that most of you, regardless your background, you know it, that AC signal can have two shapes, let me say. The first is what we call a single phase AC signal, and the second is what's called a three-phase AC signal. That's why when you go to market to search for a DC-AC inverters, you will find two types of that. You can find a single-phase inverter, which means that your output is in the form of a single phase, which is normally 220 voltage standard, or it can be a three-phase inverter that generates a three-phase voltage, and this is the commonly used shape for three phases, either in a star or a delta format. As this course is somehow a multidisciplinary course, not target mainly electrical power engineers, however, it targets different engineering directions. So we are not going to go into deep details related to that. However, of course, you can go and search for more details about three-phase and single-phase inverters. But again, let's go to the question, how we can convert a DC signal into an AC signal. The basic circuit that can be used is a very famous circuit in electronics called an edge bridge. Let's see together how this edge bridge works. So in the first cycle, you will make switch number 1 and switch number 3 on. So let's see together what will happen. As you can see here, we have 4 switches. And controlling these 4 switches determines which switches is on and which switch is off. So let's see what happens if we make switch number 1 and switch number 4 to be connected to be on, I mean short circuit, while switch number 2 and switch number 3 are an open circuit. Let's see. So I'm just going to open the annotation here, just to do some plots to help you understand the concept. Okay, so if switch number 1 is a short circuit, then you will have a pass of that. Let me make it in a different color rather than black, because black will not be easily recognized. I think maybe yellow is better, and I think we can use also a thicker line. So you will have a pass like that. So you are now connecting the positive terminal of your DC voltage with the top terminal in your coil. And what about if you have number 4 is short circuit? So the other pass will be something like that. So you are connecting the negative terminal of your voltage with the lower terminal in the coil, which simply means that your input will be directly transferred to your output. So if you have a 12 voltage, it will be transferred here as 12 voltage with the same polarity directly, as you can see. Now, in the second cycle of your edge bridge, you will alternate the switches. So you will make switch number 1 and number 4 to be an open circuit, and switch number 2 and number 3 to be a short circuit. So let's see what will happen. I will try to use another color. So now switch 2 is a short circuit. So let's check the bus together. So as you can see here, now your positive terminal is connected to the bottom terminal of the coil. Alternatively, now we make switch number 3 also as a short circuit. As you can see, your positive, your negative terminal of a DC voltage is now connected to the top terminal of the coil, which simply means that you alternate the polarity. So if the input is 12 voltage, what will reach the coil is negative 12. So by using this simple edge-bridge circuit, you can understand that you alternate your input, your signal. Sorry. You alternate your signal so that in one cycle you will get 12. In the other cycle, you will get negative 12, which simply means that you turn a DC signal to be a square wave signal, either in a positive 12 or in a negative 12. Accordingly, if this square wave signal, the nature of this square wave signal, as we already studied before, is a series of harmonics. You have a fundamental harmonic, which is this green signal. Then you have some higher frequency harmonic. So if this loop, if this square signal is filtered using a low pass filter just to pass only the fundamental harmonic and to get rid out of other harmonics, what you will get is simply this green AC signal. And that's by the end of the day will be the formation of a DC-AC inverters. So first, you convert a DC into a square. You filter this, you can step it up or step it down using a transformer. Then you filter this AC signal using a low pass filter just to pass only the fundamental component. However, as the filter you are using will be definitely a physical filter, I mean, it's not an ideal characteristic filter, this will include that your AC output signal may include some harmonics. And this is a very important point for those who are interested in studying the DC-AC inverters to try to minimize the harmonic effects as much as possible. And maybe we will consider this 3 or 4 slides later on when we consider the difference between grid connected and off-grid or standalone inverters. So you will have somehow harmonics, but you are trying to eliminate the effect of these harmonics somehow and keeping that your major circuit is a DC-AC, is a sinusoidal fundamental circuit and attenuating other harmonics. So this is the general concept. Again, I'm very sorry that this is a very shallow introduction for inverters because, as I mentioned, it's a multidisciplinary course. So we can expect that we have audience from different backgrounds. That's why we are just giving a very shallow introduction about inverters. So how inverters can be integrated in our PV system? This can be in one of 2 shapes, either in a standalone shape or in a grid connected shape. And actually, this different class distinguish the performance of your inverter 180 degrees. Because if you are going to consider it in a standalone system, then simply speaking, you are the master of the process. There is no restriction applied. So you don't have any restriction. It's only your load. It's a standalone. So you can manage to have whatever voltage range you need, whatever harmonics range you accept, whatever limitation you need. There is no governing force to control your process. You are the designer who choose your process. So simply here, you are connecting your loads based on the requirements of your load in terms of power, energy, accepted harmonics, whatever it is. However, whenever it comes to be connected into a grid, now you are not the one who mastering the process. You have to be synchronized with grids in terms of voltage levels. So for example, I'm going to connect one at 380 intermediate voltage or medium voltage. So I have to design that with a three-phase inverter to be 380 voltage. You have to connect it with a 50 hertz frequency. So your output is 50 hertz. Or it's 60 hertz network. So your output is 60 hertz, and so on. So here, the governing force coming from the grid. And here we introduce a very important concept, which is this bidirectional arrow, or what we call the net metering. Just see here, as you can see here, you are now a one directional relation. You, as a PV system, give energy to your load, full stop. However, herein, you have a bidirectional process. You can give energy to the grid, and of course, you still can accept energy from the grid. That's why we call this as a net metering. A net metering is a bidirectional relation between the renewable energy source, which is a PV array in our case, for example, and the grid. So I can give my extra energy to the grid, and still, of course, whenever I have shortage or during light loads or whatever, I can acquire or gain energy from the grid. That's why it's a bidirectional metering. But in this case, it's a unidirectional process. Or whenever we have our standard residential condition, we are a unidirectional metering. In a standard residential or even commercial conditions, we are just getting energy from the grid. We are not providing energy because we don't have any renewable energy sources in our houses or in our industrial partners or whatever. But whenever you have a PV array, you are now a supplier slash a consumer based on what we call a load profile, which we will discuss maybe in the next lecture when we consider our first technical economic visibility studies related to sizing a PV system. So this is simply how the process will go live. And this is a very important process. If you come to our title of our module, which is a PV grid connected systems, so we can easily understand that this is the system to be investigated in our course. How to make a PV array that is integrated with the utility to supply a certain AC load. So if the load and the PV are matched, then you will have direct relation or direct flow, and nothing will be nothing will be consumed or feed to the grid. If you have a shortage, then part of your energy will be get from a PV, and another part of the energy will be feeded from the grid. If you have an extra energy, then you will provide some of the energy. Then you will provide some of the energy to the grid. So it's a bidirectional process that controls the flow of the energy either to the grid or from the grid. And this bidirectional process simply depends on the energy you are producing using a PV array and the energy you are consuming using the AC load. The energy balance between these two blocks are or carrying the answer of the question. Are we going to feed the grid with extra energy, or we are going to come to get from the grid our shortage energy, or it's a zero balance process, so we are not going to get to supply the grid or to get from the grid. This is simply the process. Of course, we are going to investigate in very more detailed manner in the next lecture how this process is going to be implemented and how we can size the wattage of each of these blocks in order to have a system. And as it's a design process, so you can never find a model answer. This model answer or this answer of this question may differ based on the critical level of your load. Are we considering a critical load or not? The cost or the budget of the project, the location we are implementing the PV array, and a lot of other parameters as well. So that's all for this quick lecture related to an introduction for DC-AC inverters. Maybe we will have a very short lecture about storage system, and then we will going to turn to the next important part of our module related to sizing a PV system, which lead us to the final part of our course related to the economical analysis for that to reach what we can call a techno-economic visibility study. Thank you very much, my dear students, and see you in the next lecture.